Today we're going to start with section 6.1, which is the set of rational numbers. And we need a little bit of vocabulary in order to have conversation that makes sense, to make sure that we're using the vocab in the same way. So to start with, a fraction. A fraction is actually any number of the form a over b, as long as b is not 0. Okay? So you can talk positive numbers, you can talk negative numbers. They could be decimals, they could be square roots. Those are all considered fractions. The numerator, of course, is the number that's on top, and the denominator is the value that's on the bottom. But if you want to talk specifically about rational numbers, you have to have an additional condition that you don't have when you talk about fractions. So while fractions can have anything on the top and the bottom, say for 0 on the bottom, rational numbers have to be able to be written so that it's an integer on top and an integer on bottom. So you can't have pi over 4, right? That's not rational. You can't have square root of 2 involved in the problem and consider it rational. Now, you could have a decimal, like let's say you had 1/2 or 0.5 over 4, something like that. Okay, that's fine. But it could be changed, and it could be written in a different way to still be written as an integer over an integer. Okay, so there's things you can still have, and they're sort of acceptable because you can manipulate them, and there's things that you can't. There are several uses of rational numbers. The first use of rational numbers is as a solution. So for instance, you could solve, they can be used in solving equations like 2x equals 1. If you don't have rational numbers, there's not an answer to this problem, right? X needs to be 1/2 for this to work. If I only have integers, whole numbers, those kinds of things, I can't solve this problem. A partition is another use of rational numbers. So for example, 1/4 of my paycheck pays my gas, my rent, or my whatever you want to say. 1/4. It's a portion or a partition of a greater value. Ratio is another example of a use of rational numbers. For example, the teacher-student ratio. You guys hear that kind of stuff all the time, right? Teacher-student ratio is 1:8 or whatever. Okay, gives you a way of comparing values. And the last one that we're going to talk about is probability. So probability, which we will have a whole chapter on probability later on. An example of this would be something like this. When you roll a die, okay, this is like a standard 6-sided die, just the one that we use in games all the time. Okay, so when you roll a die, you have a 1/6 probability of rolling a 5. Okay, so those are some examples of uses of rational numbers. So the first example I'd like for us to take a look at is a visual way of thinking about fractions specifically. And these are fractions that are rational numbers for the sake of what we're talking about. So I've seen pictures like this come home on my 5th graders' math stuff. These are the exact kind of things that I see. And they make the typical mistakes that I've been saying for years now that people would probably expect a kid to make. So if you look at problem A, B, C, and D, I want you to take just a couple minutes here, maybe not that long, but go ahead and write down what you think the fraction that's representing the shaded in portion is. All right? You can always change it if you happen to have counted wrong or interpreted wrong or something like that. So just write down what you believe the answer to be in each of the cases. What do you think the fraction is for part A? 1/6. If somebody were to interpret this wrong, what do you think they might think? 1/5. So why would 1/5, or I'm sorry, 1/4 would be what I would guess. I'm sorry, I was already on the next one. 1/4. 1/4. Why might they think this is 1/4? Yeah. There's 4 boxes, right. So what is the key in order to deciding that this is 1/6? What do you have to do? Yeah, they have to be equal parts, exactly. I have to take the diagram and all the parts that I see have to be equal. So I might actually drop in these additional, line segment pieces right here like this to say, hey, look, now all the boxes are the same size, at least visually speaking they seem to be, and there's 1 out of 6 of those equally sized boxes shaded in. How about B? What is the actual correct value that you suppose to be true about B? It's 1/4. Okay, but if I do the same sort of reasoning that I did on part A, I might say what? Might say 1/5. There's 5 boxes, right? One of them shaded in. Of course, the problem is that the boxes are not all the same size. The boxes on top are smaller than the boxes on bottom. So not only do I need to sort of drop in these additional pieces that show what it should look like, I almost have to erase what's there, right? I almost have to sort of say, no, these are not supposed to be here. I really kind of don't want this, right? I don't want to think about it like that. And in order to make them equal boxes, I've got to do something like this. And say, oh, look, now the boxes are actually the same size. Yeah. What about part C? Do what? 2/7. As long as you're counting carefully, there's no problem with this one. But this is one of those pictures that people often just assume without counting, oh, well, it's 2/8. I split it into 8s all the time, just split it in half and half again and whatever. And so I think pizzas. How many pizzas are split into 8s? Almost all of them. A lot anyway are split into 8s. So it's a common imagery. So just sort of brushing aside and moving too quickly, it's an easy one to mess up. All of the first 3 are examples of area pictures. Like I've got a portion of the area and I'm taking a part of a whole. Part D is not the same kind of a picture actually at all. It's part of a set. So I've got sort of these objects and some of them count in some way and some of them count in another way. So what portion of part D is shaded in? 7/12. Yeah, it is 7/12. So I've got 7/12 of the picture over there shaded in. And that can be hard for kids too because there's actually like 12 whole objects. It's not like a whole object split into 12 pieces, and that feels different. Somehow it's not quite the same. But it's a partition, right? Like the other example that I mentioned before, as opposed to a part of a whole, it's part of a collection of objects instead. So a little bit of history for you about fractions. Egyptians actually used fractions. That's a really long time ago. Like Joseph, right? Pharaoh, stuff like that, pyramids. They actually used fractions that had numerators of 1, specifically numerators of 1. So they didn't actually write down fractions like 7/12. They would have written them as a sum of fractions. They would have added to 7/12, but they would have only expressed them as a sum of fractions that had numerators of 1. Very different way of thinking about it than we do. So they would have written it as 1/4 plus 1/3. It's different, right? The Greeks, The Greeks adopted fractions with denominators of 60 from the Babylonians. This is still what we use when we measure angles, right? 60 degrees, 360 degrees, in a circle, that kind of stuff. Portions of the number 60. And then the Hindu actually developed our modern bar between the numerator and the denominator, which came into use in Europe in the 1500s. Fractions have been around for a really long time, really, really long time. And just for the record, fractions are introduced to kids in elementary school really early. Like, I remember things coming home from my kids of identifying, like we did on that first page there, especially those area diagrams, kind of identifying in second grade. Okay, and they're not adding and subtracting and things like that. That's what my fifth graders are still working on right now. But the idea of identification and understanding of what fractions are, second, third grade these days. So it's hard sometimes for us to imagine that because, curriculum is ever changing, right? It is. And so it comes into play very early. Now, I mentioned before these different kinds of models of fractions or pictures that represent fractions. The first one I mentioned was an area model. So area model says use of a rectangle. It doesn't have to be rectangle. We used a circle in the other picture too. But rectangle is very common. And so what happens is that you use this rectangle and you somehow subdivide it in different ways. So for example, if I wanted to do the number 3/4, I would take my diagram, that's a rectangle, and I would split it in half, and in half again like this, roughly speaking. And then for 3/4, what would I do? Yeah, I'd shade in 3 of my 4 boxes, so something like that. Oh, I put that in the wrong spot. Zoomed out a little too far, let me shift it up. There we go. Sorry. Okay, so use of a rectangle. I really like area models. I think visually it feels very natural. This is where my kids actually started in 5th grade. This is always fun when I happen to be teaching something that my kids are currently doing because I can kind of give you some ideas of how I see it used right now. This is where they started this year when they were working with their imagery. They started with pictures of area models and talking about adding and subtracting things that had different denominators and whatever within an area model. They have moved on to number line models, and I would be lying if I told you they understood number lines at this point, because they absolutely do not. We have been working on it now for at least 3 weeks, and it's still really hard for them. But here's the idea with a number line. So the number line model is the idea of having a starting and an ending spot, and we're still going to do the fraction 3/4 just to say we've compared them basically. So, you've got 0 here and you've got 1 here. And for 3/4, I need to split it, kind of like I did my area picture, into 4 pieces. So that's 2 pieces, and I split it again into 2 pieces. And then to do the 3/4, I need to move over 1, 2, 3. So I'm right here when I'm at 3/4. That's 3/4. Now I'll tell you, the problem that my kids are currently having is their images already start out with the hash marks. And I feel like maybe if they had to draw them, it might help to concrete their level of understanding. But the image is already there. And not only is the image already there, it's already there in eighths. So when you find 3/4 when the image is already in eighths, that's a different level of complexity, and they struggle with that. So they're currently learning to add and subtract with number lines right now and rational numbers. The set model. I mentioned the set model a minute ago. The set model is when you have something like, again, we're doing 3/4, those chips. So you have 4 chips. They could look better, but pretend for a moment. I have 4 chips, and then 3/4 of them mean that 3 of them, wow, told it to use yellow. 3 of them are actually shaded in. Not the best picture, but you have the right idea, right? 3/4 of my chips are counted. You can do that with coins really well. So if you're using like pennies or nickels, something really cheap, right? And you happen to have so many pennies and so many nickels, what ratio or what percentage or however you want to describe it, what fraction, so we're really talking about what fraction of them are actually nickels. Well, 3 out of 4 of them are nickels, that kind of thing. So you can use coins. Some people also like to use poker chips where they put a dot on one side, like a sticker, and so they can be flipped back and forth really easily. And so you can see that, or ones that sometimes are even already colored, so they're markers, they're actually red on one side and black on another. We use those as well sometimes, and so they can be used to talk about it like this as well. There is limited usability in this. For example, if the image that you have already has 4 coins, let's say for a moment, how do I say what is 3/5 of 4 coins? That's messy, right? We can do 3/4 of 4 coins, no problem. But 3/5 of 4 coins somehow doesn't really visually work very well. So there's this sort of nuance that doesn't, I mean, we can do 3/5 on the number line. We can do 3/5 on the area model, no problem. But doing 3/5 on a set model that already has a set number of objects is much more tricky. All right, let's finish this page and we'll pause for the day. Fundamental law of fractions. The fundamental law of fractions says that if you have a fraction a over b and you have any non-zero integer, that you can multiply the numerator and denominator by that same non-zero integer and it doesn't change the value of the fraction. And of course, the whole reason we want to do this, at least at the beginning, is so that we're able to add fractions that don't have the same denominator together. Okay? It works in reverse as well. So if you have something that's an over bn, you can also reduce, simplify, cancel out, right, the n's because they match. Simplest form, that's where it comes into play. So if you have a rational number a over b, then it's in simplest form if the greatest common divisor between a and b is 1. Basically, it just means they don't have any factors in common except for the number 1. So can they both be divided by 2? Can they both be divided by 3? If so, we do so until we can't do that anymore, and then we would say it's in simplest form. All right, we'll do this example and then we'll stop for today. We're going to write 3 fractions that are equal to 7 over negative 14. So the first one that you may not necessarily think of, but it's actually a different fraction that I would like to write down, is you could write negative 7 over 14. That's the same thing, right? Absolutely is. Somebody tell me something else you could do to change this that would give you an equivalent fraction. You could divide both the top and the bottom by 7. So you could have 1 over negative 2 or negative 1 over 2, either way. What else could you do? You could multiply it by something, right? So if you want to multiply 7 over 14, you can, but you could also multiply the 1 over 2 because it's already equivalent, right? So you could do like multiply by 5. So 5 over negative 10. They're all equal to one another as long as you do the same to the top that you do to the bottom. And that's actually what happened on the first one, is that I multiplied negative 1 by the top and the bottom. Did you see that? I didn't really just move it. I mean, I did, but the reason it works is because it's the same as multiplying by negative 1 on top and bottom. All right, we will pick up on our next page when we come back next time.